Hello, everyone, and welcome back to our channel. And today we are going to look at the interesting chapter of direct and inverse variation. This is a chapter that is very useful when we are thinking about any mathematical or physical values. Say we're looking at time and speed, we're looking at how much work is required to be done by a couple of people, or how two values interact with each other in any sort of a scientific subject. Previously, in class 7, you have already learned about how to solve simple life problems by using the unitary method. And while solving these problems by the unitary method, you must have noticed that increase or decrease in or any kind of a variation in one quantity would lead to an increase or decrease or inverse of the other quantity. And in this chapter, we will get into that a bit more to understand how these variation works in the day-to-day situations. So let's start with a very simple example. So let's say if 2 pence cost 10 rupees, then 4 pence would cost twice of it, that is 20 rupees. And 1 pen will cost 5 rupees. So this means more pen, more cost, or less pen, less cost. So this is something called directly related or a direct variation because they both are directly linked to each other. Let's take another example. So if say 2 men can finish a job in 4 days, then 4 men can finish the same job in 2 days, and one man would need to do it in 8 days. So this means two things. More men would need less days, but less men would need more days. So this is an indirect relation. And this is the basis of this chapter. This is what we need to understand and apply in every word problem that we get into. So let's first look at direct variation. So let's say there are two quantities. So they vary directly if variable 1 increases when variable 2 increases, or when variable 1 decreases, variable 2 also decreases. So this is the direct variation relation as we looked at in the pens and their cost scenario. Let's look at a couple of more examples other than the pens. So say when we look at the scenario of work being done. So when we have more work, then more time is needed to do that work. And when we have less work, less time is needed to complete that work. That's how it goes. Another example would be when the distance covered by a moving object and how that distance is related to its speed. So if the vehicle is running on a more higher speed, then more distance would be covered in the same time. So more speed, more distance covered. These were a couple of small examples that we could have a look. But the things would get more clear when we look at some of the examples of direct variations through our word problems. So our first question for direct variance is that a tower of 24-meter height casts a shadow of 16 meters, and we need to find the height of a tree that casts a shadow of 12 meter under similar condition. So what we see over here is let's assume that the height be x meters, height of the tree needed. And from our question and how it's framed, we have established a direct relation for the height of the tower and height of the shadow. It's directly variational with the height of the shadow. So let's write that down, height and height of shadow. So we have for the tower, it's 24-meter. Then we have 16-meter of shadow. For tree, we have written it as x. And then we have to have a shadow of 12-meter. So for direct proportionality, we find the constant. And in this, it's x. It's height by height of shadow, which is going to be 24 by 16. This remains constant. So therefore, it would be same as x by 12. Then we'll solve for x, and this comes out to be 18 meters. Therefore, the height of the tree that casts a 12-meter shadow under similar condition would be 18 meters. So the next question we come across is that the scale of a map is given as 1 is to 200,000. And two cities are 3 centimeters apart on the map, and we need to find the actual distance between them. We have already been given the direct variational constant, and that is 1 by 200,000. So this is the distance on map, and this is distance in real time or actual distance. So as we have the constant, let's assume that the distance between the two cities is x. We have to make sure that this is all in centimeter. So that is 1 centimeter by 200,000 centimeter. We have to always keep the units same when we are working with these kinds of proportions. So we will know that constant is equal to 1 by 200,000 is equal to 3 by x. We'll solve for x to get 3 into 200,000. And as I already mentioned, this is all in centimeter. So that is 600,000 centimeter. Now we need to convert this centimeter into kilometer. So as we know that 1 centimeter is equal to 1 by 1000 into 100. This is to convert into meters and this is to convert into kilometers. So this becomes 1 by 10 to the power 5 kilometer. And well, we'll divide it as this: 600,000 divided by 1000 into 100, and this comes out to be 6 kilometer. So the distance between the two cities is 6 kilometers. Let's try this one final example before we move on to inverse variation. So if 3 men or 4 women can earn 480 rupees a day, we need to find how much will 6 men and 11 women will earn in a day. Let's start with comparing the earnings first. So earning of 3 men is equal to earning of 4 women. Earning of 1 man would be earning of 4 by 3 women. So earning of 6 men would be 4 by 3 into 6 women. And we can also link this to as earning of 8 women, because we have just doubled the values 3 and 4 to 6 and 8. So we need to find the earning of 6 men and 11 women. And this has been asked in the question. So we'll convert this 6 men and 11 women to all women. So we know that earning of 6 men is 8 women. So that would be earning of 8 plus 11 women, or earning of 19 women. So let's calculate. We already have a constant. 4 women earn 480 rupees, and that is the constant. And taking that constant, we'll have 19 women will earn x rupees, or 6 men plus 11 women would earn this much. We'll solve for x, and this gives us 19 into 480 by 4, and this comes out to be 2,280 per day. And that is our answer. So let's move on to our next section on inverse variation. So inverse variation, we have two quantities that when variable 1 increases, variable 2 decreases. Or if variable 1 decreases, variable 2 increases. So that's the crux of the inverse variation rule. So some examples of this might include: it takes a lot more time for lesser men or women a particular work done. So more people at work would take less time to finish, and less people would take more time to finish. Similarly, the speed of a moving object varies inversely to the time taken to cover a certain distance. So more speed, that means less time taken to cover the distance, or less speed means more time taken to cover the distance. And that's the some simple examples based on it. Let's do some quick word problems to understand how this all fits in together. So say 8 pipes can fill a tank in 2 hours. So how long will it take for 5 pipes to fill the same tank? So for inverse variation, we know that the two variables that are inversely variable with each other have a constant of, of the multiplication of those two variables. So our constant would be, in this section, 8 pipes into 2 hours. That's our constant. And we'll take the value of the time taken to fill the tank with five pipes to be x. We can also convert this hours value to minutes value to keep everything a lot more simple. That becomes 120 minutes. So because the constant would remain the same, we will have 8 pipes into 120 minutes equal to 5 pipes into x minutes. We'll solve for x to get 8 into 120 divided by 5, and that comes out to be 192. That means for 5 pipes, it takes 3 hours and 12 minutes to fill the whole tank. So now we have a question where we have two person who could fit a new window in a house in 3 days. If one person fell ill before the work started, how long would the job take now? And how many persons would be needed to fit the window in one day? So let's work on the first scenario. So in this, we have been told that there are two people who can finish the job in 3 days. So when we think about the number of people and the work needs to be done, so more people would mean less time taken to finish that work or less number of days to finish that work. So this is an inversely related problem. So we'll have a constant. That means two people would finish the work in 3 days. So in the first scenario, one person fell ill. So the number of people left to do the work is one person. And that will again link to the constant. So let the number of days be x. So we'll have constant equal two people into 3 days equal to one person into x days. We'll solve for x, and x comes out to be 6 days. In the second scenario, we need to find how many people we will need to fit the windows in one day. So we'll again use the constant of two people and 3 days. And now we have the number of days in this scenario as one day. And let the number of people be x. So we'll follow a constant, which is two people into 3 days equal to one day into x people. We'll solve for x again, and that gives us 6 people. So we'll take 6 people to fit the window in one day. So in this question, we have a hostel that rations for 150 students for 60 days. But after 12 days, 30 more students join to the hostel. So we have to find out how will the remaining ration last. So let's start by following the word problem. So we have 60 days ration for 150 students. And everything was well and good for the first 12 days. And after 12 days, the scenario changes. So we have, after 12 days, we have 48 days, that is 60 minus 12 days, 48 days of ration for 150 students. And in this, we have new 30 students. So our new number of student is 150 plus 30, and that is 180 students. And we need to find how many days of ration is left for 180 students. So we'll again find the constant 48 days into 150 student. And this would be equal to, again, x days for 180 students. And now we'll solve for x. And then x finally comes out to be 40 days. So our new rationing would be 40 days for 180 students. And that's how we solve this question. If you like our work, don't forget to like, share, and subscribe for more. See you.